Hello, student. Welcome to this session, uh, Electricity and Magnetism. This is session 20. And in this session, we are going to study the Amperes Circuital Law and applications of Amperes Law to a straight wire and solenoid and toroid. So the learning objectives are Ampere's circuital law statement, and it will be given, and proof will also be done, and application of Ampere's law to a state conductor will be tested, and also will similarly apply the Ampere's law to the solenoid and toroid. And at the end of this session, the statement and proof of the Ampere's circuit law will be given, and also the expression for the magnetic field due to a straight wire using Ampere's law will be derived, and also the derivation of the magnetic field due to a solenoid using Ampere's law will be done, and also we are going to derive the expression for magnetic field due to a toroid using Ampere's law. Prerequisites. In the earlier sessions, already we have discussed the expression for magnetic field due to a straight wire, and also we have discussed the magnetic field due to a circular coil, and also we have discussed the magnetic field due to a circular path. And in this session, I am going to define the solenoid and toroid. So this is the Ampere's this is the Ampere's circuital law. Sorry. So here the statement of the Ampere's circuital law is given by like this. The line integral of the magnetic field B around any closed path is equal to mu naught times the total current enclosed by that path. So you can see here, this is a straight conductor is there. So this closed path is there. Here we have considered a closed path. So the closed path, then the magnetic field due to this closed path is nothing but the closed integral or the line integral of the circular path is to be done, and that will be always equal to mu naught times the current flowing through that closed path. So for proof of this uh, Ampere circuit law is done like this. Consider a long straight conducting uh, straight conductor carrying current I in the direction as shown in the figure. So here in the figure, this is the straight conductor and this is the direction of current. The magnetic lines of forces are concentric circles uh, centered around the conductor. So these are the magnetic lines of forces. They are centered around the conductor, and we know that the magnetic field. We know that the magnitude of the magnetic field at a point P at the distance of r from the conductor is given by this equation, that is B is equal to mu naught I divided by 2 phi r. So this we have to prove. And consider a magnetic lines of force of radius r. On this circle, magnitude of B is same every point and is along the tangent to the circle. Here you can see in this diagram, I have considered a magnetic lines of force, which is a circular one, and this is the center of the circular path, and we have considered a point at a distance r, which is the radius of this circle, and that means here we are considering elemental path dl. So at this point, the direction of magnetic field is in this direction, and along this path of the circle, this magnetic field is uniform. Wherever you measure it, that will be a constant value, and the direction of the magnetic field along this circular path is going to change at every point. So that is given by the tangent on that line, on that circle. So on the circle, the direction of the magnetic field at every point is having a different direction. So here it is in this direction, and here it is in this direction. So therefore, the tangent to the circle at a given point on the circle gives the direction of the magnetic field. And at this point, you see the angle between B and DL is 0 in this case. DL means the elemental path I have considered, and at the same point a tangent is drawn, and since both are parallel, the angle between this B and this DL is 0. The angle between B and DL is 0. Then what happens to this closed integral of B dot DL? So this closed integral of B dot DL, it is a dot product, so it is written as B dl cos theta, and this theta is 0 as I told now, and this becomes closed integral of B dl cos 0. Cos 0 is 1, so this can be written as B into closed integral of dl. Then substituting value of B from equation 1. Equation 1 is here. This is the equation 1, and here you substitute the value of B. So this now closed integral of B dot dl is equal to B. B is there. B is now mu naught I divided by 2 phi r from equation 1 multiplied by closed integral of dl. But closed integral of dl is equal to 2 phi r, which is the circumference of the circle. So you substitute that value, then we will get like this, and therefore closed integral of dl is equal to mu naught I divided by 2 phi r, and this is the value of closed integral of dl. So this is also 2 phi r, and 2 phi r get cancelled, and this is equal to mu naught I. So hence the Amperes law is proved. Now we will apply this Amperes circuital law to the straight wire. So for that you consider a long straight wire carrying a current I in the direction as shown in the figure. So again you consider like this, consider a straight wire which is carry some current in this direction, carrying some current in this direction. So the magnetic lines of force are concentric circles, all centered at the conductor. So this is, for example, one we have shown one magnetic lines of force. Like this, all the magnetic lines of force are encircling this conductor, and they are centered at the conductor. Choose a circle of radius r as the closed path. Here I have chosen a circle of radius r. Here we have shown this is the radius r. So we have chosen a circle of radius r as a closed path, and let B be the strength of the magnetic field at a point P, which is at a distance perpendicular r from the conductor. So here we have considered a point P. This is a point P. At this point P, and this point P is at a distance of r from the conductor, and this is a tangent drawn at the point P. Then the angle between B and DL is 0. This angle between this B and this the elemental circular path considered here is 0 because both are parallel. So therefore, applying the Amperes law to this closed path, we have closed integral of B dot dl is equal to mu naught I. So this dot product is written as B dl cos theta, and theta is 0. So this equal to mu naught I, and or this is equal to B into closed integral of dl, because cos 0 goes 1 is equal to mu naught I. And as we have already seen that the value of this closed integral is 2 pi r, so therefore it is b into 2 pi r is equal to mu naught times I, or b is equal to mu naught I divided by 2 pi r, gives the magnetic field at a point due to a straight wire using the Ampere's law. So this one application is done. Next, we will apply the Ampere's law to a long solenoid. So for that, consider a long air-cored solenoid having closely packed coils. Now I am defining the solenoid. Solenoid is simply a copper coil. When the number of turns in the copper coil is too large, then the length of the coil becomes too is very large as compared to radius of the coil. Such a bigger coil is called as a solenoid. Here you can see actually it is a part of a solenoid. So when the length of a coil becomes large, very large compared to its radius, that kind of coil is called as a solenoid. So that kind of solenoid we have considered here. Let I be the current flowing through the solenoid, n be the number of turns per unit length, and choose a rectangular path ABCD in a long solenoid. So here we have chosen a rectangular path ABCD on the solenoid such that AB is equal to L. Then the line integral of V over the closed path ABCD is given by this equation. Closed integral of B dot dl is equal to, it is integral from A to B dot dl plus means we have to consider magnetic field due to every side of this rectangular path, because this rectangular path is having four sides. So therefore the magnetic field uh, due to every side is to be added. So it is written in this way. Then we have to check what happens to each term, this kind of terms. Now A to B dl cos 0 means due to the side AB, this is equal to B into A to B dl. Cos 0 is 1, so this becomes a BL. So this is the value of the first term, and the second term goes to 0 because the angle between B and DL is 90 degree. Similarly, the third term also goes to 0 because the angle between B and DL is 90 degree, and cos 90 is 0. And this term, this side CD is also 0 because this side CD is out of the solenoid, and out of the solenoid magnetic field is 0. So therefore we are left with only this much. Therefore the closed integral of B dot dl is equal to closed integral from A to B dot dl. So this is equal to BL. We are so the magnetic field produced by the net magnetic field produced by uh, this rectangular path is only B into L. Then according to Ampere's law, closed integral of B dot dl is equal to mu naught times the current enclosed by rectangular path ABCDA. So the current enclosed by this rectangular path ABCDA is calculated in this way, and the effective length is only AB, that is L, and number of turns per unit length is the small n. Then the total number of turns will be equal to n into L. Therefore the total current enclosed by rectangular path is equal to NIL, and this equation becomes like this. This is BL is equal to means this equation becomes a closed integral of B dot dl is equal to mu naught times NIL. You have to substitute NIL here. Then compare this equation and this equation, which is a closed integral of V dot dl is equal to BL. Two equations are there. LHS are same, therefore RHS are equated. and RHS of this equation is BL, and RHS of this equation is mu naught times NIL, and here LL get cancelled, so we are left with B is equal to mu naught NI, gives the magnetic field due to a solenoid. Note that the magnetic field in the solenoid is proportional to the applied current and the number of turns per unit length. So in this way, we calculated the magnetic field due to a solenoid. Next, we'll apply the uh, Ampere's law to a toroid. This is a toroid. Toroid is a long solenoid bent into a circle with the ends joined. So you can see here, this is a solenoid actually. This is a solenoid, but it's when the two ends of the solenoid are joined together, it becomes a toroid. Hmm. And since the axis of the resulting solenoid is a circular, the lines of B are also circular, and the direction of B is tangent to the circle passing through the point, and concentric with the toroid, and B is same at all points on such a circle. So the axis of this solenoid is a circle like this. So when the solenoid is joined, is bent into a circle, then the axis of the solenoid becomes a circle. So therefore, the magnetic field on this circle is again given by a tangent drawn to it. So just like then the case turns to a circular path, just like the when a current carrying circular path is there, the magnetic field produced by the circular path is obtained by drawing a tangent at every point. So the case turns like that. So therefore, consider a point at a distance of r from the center, lying within the space enclosed by the windings of the toroid. So actually, this is wrong. Point is considered here. So I am considering the point here, so that the distance between the center of the coil and this point is r, and then let the capital N be the number of turns and I be the current flowing through each turn. So therefore, total current I naught is equal to Ni. And according to Amperes circuital law, uh, closed integral of B dot dl is equal to mu naught I naught. Actually, I it is here, it is taken as a I naught, and I naught value of I naught is Ni. Substitute here, so it becomes mu naught Ni. And closed integral of dl is written as B dl cos 0, and this is written as a closed integral of dl. Its value is 2 pi r, so it is B into 2 pi r. Therefore, B into 2 pi r is equal to mu naught times Ni. Mu naught times Ni. Both are equated, and therefore it becomes B is equal to mu naught In divided by 2 pi r, gives the magnetic field due to a toroid. If n is the number of turns per unit length, then the total number of turns will be capital N, that is equal to n into 2 pi r. So then in this equation, you substitute the value of capital N, then it becomes mu naught In into 2 pi r. So this 2 pi r get cancels. Again, it becomes equal to mu naught Ni. Again it becomes equal to mu naught Ni. So this is equal to mu naught Ni. So therefore, mu naught Ni gives the magnetic field due to a toroid. Note that the magnetic field due to a toroid is zero at all points except within the core. So it's all about toroid. Next, we will move to some problems. A solenoid of length 1.5 meter has a radius of 2 centimeter, in which contains three layers of windings, each of 1200 watts. If the current in the solenoid is 8 ampere, calculate the value of the magnetic field intensity at the center of the solenoid and also calculate the magnetic flux through the cross section at the same point. So here L is there, R is there, and N is there, I is there. So B is given by mu naught Ni, calculate B, and magnetic flux uh, phi is equal to always it is B into A. So B into A is calculated. So this is the flux flowing through this solenoid. And Ampere's law, MCQ, Ampere's law is given by, these are the options. The answer is closed integral of B dot dl is equal to mu naught I. As I studied, option is the B. Sorry, it is not J, it is wrongly typed. It is, this is, sorry, this is B. Option is C. Option is C. Closed integral of B dot dl is equal to mu naught I. Next, MCQ2. A current of 1 by 4 pi ampere is flowing in a long straight conductor. The line integral of this of the magnetic induction around the closed path enclosing the current carrying conductor is given by. So these are the options. The answer is 10 to the power minus 7 Weber per meter. Magnetic field inside the solenoid is, options are 0, weak, uniform, non-uniform. It is uniform. So magnetic field at the solenoid, except at the ends, it is uniform. It is taken as a uniform. Only at the ends slightly it changes. Compute the magnetic field of a long straight wire that has a circular loop with a radius of this, and 2 ampere is the reading of the current flowing through this closed loop. So these are the options. So it is the case of magnetic field due to a straight wire. It is a straightforward problem, and it gives a value of magnetic field equal to 8 in 10 power minus 6 Tesla. T is the unit of a magnetic field. And find the magnetic field intensity at the radius of 6 centimeter of a coaxial cable with an inner and outer radii are 1.5 centimeter and 4 centimeter respectively, with a current flowing of 2 amperes. So this is also this can be calculated, and this gives out to be, and the answer is 0. So this is about this chapter, and I hope you enjoyed this. Thank you.